All of you have joined. Have you finished your activity?
Yes, ma'am.
Okay, that's good. I thought it would take you longer than that, but good. Let me just check. Okay, so there are just 3 or 4 students still working on it, but we'll begin. It's time. Any questions regarding the activity?
Yes, ma'am. I didn't have enough time to finish it. The first 4 question was the long question, and after that, the multiple choice question. So the easy ones was in the end, so I couldn't finish it.
Okay. I'll open it for you to finish it later. Anybody who finished it and had any questions? Because if you started late, like after 2 p.m. later, like 10 minutes later, then obviously you would not have enough time. As I mentioned in my email, you would need at least 25 minutes to finish that. All the questions were clear, those who were able to finish, because I do see a lot of you have finished. Lots of blanks though. Sirat, were you able to finish it all? Sirat is not here. Atik, were you able to finish?
No, teacher.
Okay. When did you start, Atik?
2 p.m.
You started at 2 and you could not finish? Okay.
Yeah.
Abhishai? Was you able to finish, Abhishai?
No, I wasn't able to finish in time.
Okay. Let me see.
The second, third, and fourth question needed some more time.
Mm-hmm.
Yes.
Sia, were you able to finish? Okay, almost everybody has left those long questions blank. How about take, let's do those questions in the class together. So the two long answer questions, let's work on those. So question number 2 and 3, 2, 3, and 4. Okay. We'll do 2 later. We have a similar question in our class activity as well. So let's do 3 and 4. Start, do question number 3, and then I'll do it. Done?
Yes, ma'am.
This was the question. Anybody knows the median, sorry?
The median is 23.
Is everybody getting 23?
Yes.
Yeah,
Yes.
let me quickly arrange the data. So it would be n is equal to 16. So it will be between 8th and 9th data points. So the mean of these two is 23. Okay, that is median. What is Q1?
Professor,
Mhm.
there is 37 in the data set.
Oh, okay. So, okay. 4, 5, 6, 7, 8. Yeah, it still comes here. 23 median. What is Q1?
14.5,
14.5. Q3?
31.5.
31.5. So what is IQR?
17.
That is Q3 minus Q1. Okay. So what is the 75th percentile?
31.5.
31.5. It is Q3, right?
Yes.
Okay, write the 5-number summary. So that is straightforward. 8, 14.5, 23, 31.5, and then 40. So that is 5-number summary. This is the maximum. This is minimum, Q1, Q2 or median, and Q3. Okay, so that was that. That was simple. Let's look at this one. Take a few minutes, not too much. Try to do it as quickly as possible.
Twenty-one point five.
We found, so I found Q1, Q2, Q3. Check if I made an error or you've made an error. Find X bar, find S.
it would be 71 point, I guess, the median.
Median 71.5?
Yeah.
Okay.
Professor, is the mean 71.1? Oh, yeah. Okay.
Right? If you're multiplying all data points by 2, then the mean and standard deviation would change the same way. Any question? Okay, then moving on.
Professor, I have a question.
Go ahead.
So there was a question in previous class, I guess. You asked that there was a salary given for number of people, and then the second part of the question said that what if the salary, I mean, the owner gives 5,000 bonus to everybody? What will be the mean and the
Yeah.
standard deviation? So the standard deviation didn't change.
Yeah, because we were adding, we were not multiplying,
Oh, okay.
right? That's the property. So
Okay.
if you multiply all data points, both mean and standard deviation change. But if we add or subtract, only mean changes the same way, standard deviation does not change.
Okay.
You can test that for yourself, but we'll move on. Okay.
Sorry, ma'am. Could you repeat that again? I didn't get it.
Read the notes. If you did not, then what do I do? To finish the syllabus as well. All other sections are done with the unit 1. I'm the only one remaining. So where was it? Read. If you read it yourself, you probably will remember. If I keep reading, you'll keep forgetting. The same property will apply to median and IQR that we'll see later. Okay, so exactly same property will apply there. So we did this question in the last class. We did median and IQR the last class. And we did a 5-number summary, but we did not do a box plot. Okay, we'll do that later. So now that we know how to write the 5-number summary, we need to make a box plot. What is box plot? Box plot is basically we draw a box with the help of Q1, Q2, Q3, and then we draw some whiskers. So box plot has a box. So we scale the y-axis. First of all, that's what we do. Okay, this is the y-axis that we need to scale. So let's say 0, 10, 20, 30, 40, whatever we need, we will scale it accordingly. Okay, then we draw a box using 3 lines. And let's say one is here. What are these lines? Why are we choosing to draw these lines here? This is our Q1, this is Q2, this is Q3. And then this is our, let's say, maximum. And let's say this is our minimum. We connect these maximum and minimum with straight line with this box. This is called a box plot. So you're basically plotting your 5-number summary in the box plot. That's what a box plot is. So what I want you to do, you have the 5-number summary of data set 1 and 2. I have erased it, but you probably have it here. Use these 5-number summaries for data set 1. This is, we had data set 1, 5-number summary. Okay, make a box plot with this. And similarly, make a box plot with the other 5-number summary. I'll copy that down as well so that you can work on it. Go ahead and make box plots for each one of them. You can make them on the same graph. You can make them on separate graphs. It's totally up to you. Making on the same graph, then you'll have 2 box plots on this graph. right? Something like this. So if you have two box plots side by side, you can compare which box plot, which data set has higher median. Median for data set 2 is here, which is 68.5, or that's not what it looks like, but 68.5. And for 1 is 32. So obviously this is higher. You can see this is higher than this. The IQR seems quite similar, maybe slightly different, but not very different. This length of this box will determine IQR. This length is IQR. Right? So that's box plot, pretty simple. Moving on. What does box plot show? Obviously, it shows us the 5-number summary. If I gave you a box plot, I could ask you what is the IQR of this data set, what is the median of this data set, and so on. But apart from that, it also shows if our data is symmetrical or not. You draw the box plot. If this median cuts the box almost in the center, that means your data is symmetrical. Okay. If it cuts such that the upper box is smaller than the lower box, think about it this way. If you drew a histogram for this data, it would have shape like this. If you put it on horizontal axis, its shape would be like this. So if that is the shape, what does it look like? It's left skewed. Similarly, if the lower box is smaller, such that the tail is on this side, right? So this is the shape. So if you put it on horizontal axis, this is how it will look like. It is skewed to the right. So by looking at the box plot, we can determine if our data is symmetrical or almost symmetrical, or skewed to the right, skewed to the left. So that is an easy depiction of the skewness of our data. Moving on. Now, question comes outliers. I have mentioned outliers earlier, that outliers are data points that are either too small or too large as compared to the rest of the data set. That would be called an outlier. For example, I think I gave an example like this. If entire class scores were between 70 and 100, one student got a score of 3. Now this 3 is a very low score as compared to the rest of the class score. So 3 could be an outlier. Or on the other hand, let's say the entire class's scores were between 30 and 60 and one student got 100%. So 100 may be an outlier. But there has to be a criteria to determine if a particular data point is an outlier. How far, how large or small it must be to consider it as an outlier. And why do we care about outliers? Outliers are could be problematic data points. You know, if I'm trying to make a case that students in my class, they really do well in stats classes compared to the other classes. I'm not saying that's true, but let's say this is what I'm trying to make a case of. And I find that most of my students have gotten marked between 70 and 100, which is awesome, right? That's a pretty high mark. But then one student got 3. This one low mark will bring the average down of the class, and it will kind of I'll have to conclude that no, my average is similar to other classes' average. Because of this one student's mark, the average goes down that much. So I want to know if there's an outlier in my data set, because this 3 mark, if this is an outlier, then I will have to find out why did this student get such a low mark as compared to the rest of the class. I'll have to look at my marking guide, see if I made a mistake. Maybe I was typing 53 and my 5 key was stuck and I ended up typing only 3. That was an error, right? So whenever we see an outlier, first we see if we have made an error, so that you know, it's one way to see to correct our mistakes. But if it is not an error, then I want to see, okay, who is the student? Why did the student get this mark? And then I look at attendance record, let's say. And I find out that this student attended no classes, absolutely no classes, just came and wrote the midterm exam, but did not write any, did not attend any classes. Now, if the student did not attend classes, that does not reflect my teaching, right? There could be several reasons why a student did not attend classes. They had some personal issues going on or whatever, but that does not reflect. So I'll say, well, this student did not attend classes, so I want to remove this data point and compare my class average with other sections and see my class has a higher average than other classes. So outliers are important to be identified if they occur. We obviously do not want to see outliers, but if they are, then we should be able to find them and then investigate further why they occurred. Okay. Sometimes there is no reason, and that's a true data point. We cannot do anything about it. So there is a rule how to identify outliers. There are actually two rules, but we'll focus on only one rule. Other one I'll mention, if I remember to, is 1.5 IQR rule. This is an arbitrary rule, but it's a pretty good rule that helps us identify if there are any outliers in our data set. So what is this rule? According to this rule, if a data point is less than, if its value is less than Q1 minus 1.5 times IQR. 1.5 IQR means 1.5 times IQR. Whatever your IQR is multiplied by 1.5. Q1 minus 1.5 times IQR. If any data point is less than this, or if any data point is higher than Q3 plus 1.5 IQR, then that data point would be considered an outlier. So what does that really mean? You're probably wondering, okay, how does that make sense? Let's say this is your data set, box plot. So I'm going to draw a box plot horizontally, just to make my point. This is just, assume that this is a box plot because I'm not using any particular data for this. Okay, let's say this is minimum, Q1, Q2, Q3, and maximum, right? So I don't have the entire data set here, but let's say this is our box plot. Now, what we are saying according to this rule, first let's find what is IQR here. Let's say Q3 is 70 and Q1 is, let's say, 47. So this is 47, this is 70. Okay, so that is 23. That is IQR. So that is certain distance, right? Now we are saying 1.5 IQR would be 1.5 times 23 would be equal to, anybody can do this math quickly? $34.5. So this is a random number. It's a number that an arbitrary rule. What is this length? This length is 34.5. So we are saying any value in our data set, whatever the data set is, any value in our data set that is this much lower than Q1 or more or further down, that would be considered an outlier. So what is this 34.5 length? Q1 minus 34.5, that would be, Q1 is 47 minus 34.5. How much is that? 10.5? No, 12.5. 47 minus 34.5, that $12.5. So that is up to this point. So we are saying that any value that is smaller than this would be considered an outlier. Same 34.5, sorry, same kind of distance of 34.5 will add on the other side as well, will add to this side. So 70 plus 34.5 is 104.5. So 104.5, let's say, is here, right? So this is again a distance. This distance is 34.5, right? So any value that is higher than this, or lower than this in our data set, we will say it is far enough from our data set, the main data set, such that it can be called an outlier. So our majority of our data points should be within this, right? Yeah, this is Q1, Q2, Q3. That's where the center is. That's where the spread is mostly. So there are some values that will be higher than Q3. Maybe there are values here, 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 here. But then there are values here and here as well. And on this side, we have values only. This is the minimum, so there are no values less than this. Now, if these are a data set and we are finding that these two values are actually larger than Q3 plus 1.5 IQR, these data points would be called outliers. Make sense? So we have determined a distance. How far should the data points be from Q1 or Q3, so such that they can be called an outlier? And that distance is 1.5 IQR. Okay, that is what we are using. So we call these lines, these are not data points. Remember, these are not, they've got nothing to do with data points. These are arbitrary fences, gates. We call them gates or fences. Gate 1, gate 2, or fences, fence 2, fence 1. We have drawn these fences. We are saying that if a data point goes out of these fences, then we'll call it an outlier, right? Then it is far enough to be considered an outlier. That is that is 1.5 IQR rule. Any question on this? So why don't you go ahead and find outliers in data set 1 and 2? So this was our 5-number summary. You have the data set earlier. You should have the data set with you. So you have everything. Go ahead and find if there are any outliers in data set 1, if there are any outliers in data set 2. Shouldn't take you more than 4 minutes.
There are no outliers in dataset 1.
Say it again.
I found out that there are no outliers in dataset 1.
Okay, good. There are no outliers there. It's good.
Ma'am, sorry, what's the value of Q3 in the second data set, please?
Q3 in second 80.5. You should have it in your notes. We did it in the class.
Yep. Ma'am, there are no outliers in dataset 2.
Data set 2, you found no outliers. What are your fences for data set 2?
Fences are 183.25 and the other one is hold on, it's negative 50.75.
They're not correct.
There
What
is
is
one
the-
outlier.
Yeah, what is the IQR for the second data set?
Is 68.5.
28.5.
28.5. IQR is 80.5 minus 52.
Oh, okay.
So again, check, yes, there should be one outlier in data set 2.
Yeah.
And which is 135. Yes. Everybody quickly check, finish, then we'll move on to the next part of our class. All good?
Yes, ma'am.
Okay, so in the exam, we may ask you a question like this. Are there any outliers how many outliers are there in the following data set, right? Then you have to count how many. Or we may ask you, what are the outliers? Then you write down the outliers, right? Or sometimes we ask you, what are the fences for outliers in this data set? So we're not asking you what are the outliers or how many are there. We're asking you, what are the fences? So you just calculate Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. Okay, so be careful what is being asked, because we will give you outliers as well, and we'll give you fences and all sort of stuff in the multiple choices. And if you didn't read the question correctly, you'll still find the answer that you found in the multiple choices, but it'll be the wrong answer. So be careful, read carefully. Okay, so that is 1.5 IQR rule. Once you have 1.5 IQR rule, now we can modify our box plot to show these outliers. It's called modified box plot. It is also known as outlier box plot. So basically, this is a box plot that has been modified to show the outliers as well. So now in our data set 2, we had outliers, right? This was our box plot for data set 2. Now you told me that there is an outlier, which is 135 is an outlier. So what I'm going to do, I'm going to draw this part differently. I'll first show the outlier. Okay. And now these lines, by the way, these lines are called whiskers. Whiskers, like cats have whiskers, the mustache, the hair coming out of under the nose from cat or dog, they're called whiskers. So these are those lines. Okay, now these whisker, I still have to draw it, but my whisker should not touch the outlier. That's how we modify. If there's an outlier, we first show it as a dot, And then our whisker should not touch the outlier. If there are multiple outliers, I'll show that multiple, but we don't have multiple, we have just one. Now, how far will the whisker go? It will not go up to this, but how far will it go? You cannot just randomly draw it wherever you like. No, it has to show the maximum without this outlier. What would be the maximum in your data set if you remove the outlier? Remember, if you think that, oh, this is a mistake, we are going to remove this data point. What is the maximum now if we remove it?
89.
89. So whisker will go up to 89. The next data point in our data set that is not an outlier. So 89. This was the next data point in our data set. Remember, this is a arranged data set, right? In this is the outlier. If we remove this, if we don't consider this, what is the next data point in our data set? Largest data point, if it is on the upper side, and it's 89. If we had an outlier on the lower end as well, we'll do the same. Next data point, next smallest data point, that is not an outlier. So that's how you draw. So this length is important. And again, we will ask you questions like this. If you were to draw a modified box plot for the following data set, how far would the whiskers go? So in this case, the answer would be, the whiskers will go up to 35. This is 35, and the other one will go up to 89, not up to 135, because that's an outlier. Okay. So that is a modified box plot.
Professor,
Yes.
will there be any question like such in an exam, like where there is only given a box plot with the 5-number summary, and then we have find till where the whisker will go? How would we do that?
Yeah, you should be able to do that, right? No, if your data set is not given, then you cannot do that if there are outliers in that data set,
Okay.
right? You need to know the data set to determine what is the next data point. So no, we cannot ask that. Something that's impossible, why would we ask that? Okay, here is an example. Why don't you go ahead? This is a data set. It's not 5-number summary, it is data set. I've arranged it for you just so that's quick. So very quickly, make a modified box plot for this, okay? So all that you need to make a modified box plot, first do that and then make the modified box plot. You need to first find media, you need to first find 5-number summary, you'll need to then find out IQR, you'll need to find the fences and determine if there are any outliers, and then plot.
Ma'am, we have an outlier.
Mhm.
It is 195.
Now make the box plot and tell me how far would the whiskers go?
Uh, 20.
100.
Why 20? Where is 20 coming from?
Would it go till
Twe-
100?
Yeah, 15. The lower whisker will still go, right? There are two whiskers, so 15 and 100. There's no outlier on the lower end, so therefore it will go up to 15 there. But upper end there is an outlier. So without this, which is the largest value, is this. That's where the whisker will go. Okay. Okay. Now we'll talk about the properties of median and IQR, just like we did for mean and standard deviation. Similar kind of properties, but we'll be summarizing everything here. Median and IQR are robust measures of center and spread. Remember, mean and standard deviation are not. Mean changes very quickly towards the skewness or towards the outlier, and standard deviation increases if there are outliers or skewness. Now, median and IQR do not get affected easily by the outliers or skewness. They are pretty robust, they stay in their same place. And therefore, when our data has outliers or is skewed, then median and IQR are more dependable than mean and standard deviation. So mean and standard deviation should only be used in symmetrical data when there are no outliers. Okay. When there are outliers or skewness, then we should not be using mean and standard deviation as our measures of center and spread. We should be using median and IQR. Any country, such as in Canada, for example, our government reports the median salary, median income of Canadians households. They don't report mean income. You can search it up, they will not report mean income because it is highly skewed. A small number of people have very high income, right? There's a huge income gap, so it is highly skewed towards the right. Most people have moderate kind of income, but then there is a small proportion of our population that has very high income. So our income in Canada or United States or any part of the world for that matter now is quite skewed to the right. Small number of people have very high income. And because it's so skewed, it will be meaningless to report the mean. Mean doesn't show the center of our data. Instead, they always report median income. Okay, so mean should not be used for skewed data, and therefore standard deviation should not be used for skewed data. So when the data is symmetrical, mean and median both are in the center, we can use either, it is fine. Both are equally good. Here median is approximately equal to the mean. Okay, or is equal to the mean or approximately equal to mean. But when it is skewed to the left, then mean shifts towards the left. It gets drawn towards the skewness, so it will shift towards the left. So if median is here, mean will be on its left hand side, so mean will be smaller than the median, right? This side is less than the median. So if it is left skewed, mean is smaller than the median. If it is right skewed, mean is larger than the median. Okay, so sometimes we ask you questions like this in the converse manner. Here's the data set, and for this data set, tell us if it is skewed to left or right, or is it symmetrical, and tell us what are the mean and median. Okay, so if we are asking you to calculate mean and median, you find mean and median. Let's say we gave you a question and you found mean to be 75, you found median to be 70. What would you think based on this if the data is skewed to the right or left or asymmetrical?
It is right skewed.
Right skewed, because mean is larger than the median. Okay, so make sure you understand it, the theory of it, not just be able to calculate mean and median. You should be able to do these kind of things as well. So that is one property. We talked about this when we talked about mean. Now we have compared mean and median as well. Median and IQR have the same unit as the variable, right? Just like mean, median, standard deviation, IQR all will have the same units for a data set. When a variable is added to, remember we did this for mean and standard deviation, now we'll do it for median. When a value is added to or subtracted from each data point, median changes the same way, but IQR does not change. Just like mean does not, mean changes, but standard deviation does not change. Similarly, median changes, but IQR does not change if we add a value or subtract the value from the entire data set. But if you multiply each data point with a value, then both median and IQR change the same way. So you can conclude that so I'm just summarizing the two that we did before and we just did. When we add or subtract a value from the entire data set, the measures of center, which are median and mean, change the same way, but the measures of spread do not change. When we multiply or divide the entire data set by a number, by a value or number, both the measures of center that is X bar and median, and the measures of spread, which are, sorry, standard deviation and IQR, these are measures of spread, change the same way. Write this down and make sure you understand it and remember this. And after doing this, writing this down, work on these two questions very quickly. Find the mean, median, standard deviation, IQR for the following temperatures given in degrees Celsius. Are there any outliers in this data set? Draw the modified box plot. How far would the whiskers go? So do that. And then if the data was converted to degree Fahrenheit, what would be the mean and standard deviation and median and IQR in degrees Fahrenheit? If you don't remember how to convert in degree Fahrenheit, here's the formula. So temperature in degrees Fahrenheit is equal to 32 plus 1.8 times temperature in degrees Celsius. Okay, so these are temperature in degrees Celsius, and to convert them into Fahrenheit, this is how you would do. Use the properties that we just talked about to determine this new median and IQR and everything. Take
Uh,
10 minutes to finish both.
Ma'am, could you zoom in a little bit, please? Thank you.
Is the median 27?
I hope it is. I've not done it. Is everybody getting 27?
Yes, it's 27.
IQR is 6.
Okay. You got 26? That means I'll have
6.
to do it. Median is 6? IQR is 6.
IQR.
Okay. Yeah. IQR. Yeah, that is correct. IQR. Remember. So it must be right. Yeah.
And there is one outlier.
Mhm. Which one is that?
It is 13.
13. Okay. Okay. How far would the whiskers go then?
22 and 37.
22 and 37. Perfect. Everybody got it? What are the fences? Let's write those as well, just so that anybody who is getting wrong answers. Fences or gates for outliers.
14 and 38.
Is everybody getting these?
Yes.
Okay, nobody is having any problems. Okay, so from that, you can, any value that is less than 14 or any value that is greater than 38 in our data set would be considered an outlier. So 13 is less than 14, therefore that is one outlier. And there is no value more than 38, so there is no outlier on the upper end. So the only outlier is 13. And the whiskers will go up to the next data point, which is 22 on the lower side and 37 on the upper side. Look at your box plot. Does it look symmetrical or skew to the left or right?
It looks skewed to the left.
Skew to the left. Okay. By looking at mean, median, and mean, what does it look? This is the mean. This is the median. Comparing these, what does it look like? Left, right, or symmetrical?
It is left.
Yeah, somewhat slightly left skewed, right? Okay. Because mean is smaller. So now when you convert these into Fahrenheit, what is the new mean? Mean in degrees Fahrenheit would
The
be
mean would be 80.06.
80.06. So it will be 32 plus 1.8 times the mean in degrees Celsius, which was 26.42. So you can do the math. What would be the standard deviation in degree Fahrenheit?
42.8.
So addition has no impact, remember? We just talked about it. If we add or subtract a value from the entire data set, the measures of spread do not change. So it will be, the original standard deviation is 6.007 times multiplication will still have an impact. So times this, do the math. So it will not be 40, whatever said, that this is going to be about 11, 12, something like that. So about 11. Similarly, median would change the same way by addition and multiplication, which was 27. But IQR will change only with multiplication, not with addition. So 1.8 times 6. Okay. So that is your answer here. Now we'll begin with unit 2. So this is bivariate analysis. Unit 1 was univariate analysis, single variable. Now we are looking at relationship between two variables. Quantitative variable is what we'll be talking about. Two quantitative variables, how are they related to one another? That is called bivariate analysis or data relationship between two variables. Two quantitative variables is what we'll be studying. We'll not be comparing qualitative. That is for 3000 level or 4000 level stats courses. So quantitative variables is what we'll do. So how can two quantitative variables be related? They could be, for example, do you think there would be any relationship between children's age and height? What do you think? Do you think there's any relationship between children's age and height?
Yes.
What kind of relationship would you see? As the age increases, what happens to the height?
Height increases.
Increases as well. So both are moving in the same direction, right? Age and height, these are two quantitative variables. For children, these will both move in the same direction. And therefore, they are called positively related or directly related. On the other hand, what do you think would be the relationship between student scores in an exam and number of hours they spend on social media? Do you think there will be a relationship?
No.
No? Okay. You can test it on
There will
yourself.
be-
Probably.
That will be
The more
negative.
time, and it will be most likely a negative relationship. There may not be any relationship, but I suspect it will be a negative relationship because the more time you spend on social media, the less time you have for studying. And less you study, the lower your marks are likely to be. So that's basically what we are trying to see, what kind of relationship exists. But obviously, we'll have to collect data and see if there is a relationship. It's not just logic. We have to collect data and study those relationships if there are any or not. So let's examine the data relationship between two quantitative variables using a plot called scatter plot or biplot. Like anything else, whenever we study statistics, first thing that we do about our data is make some plots, because plots make the picture a lot clearer. So the plot that we make for looking at data relationship is called scatter plot or biplot. So here's some data, number of hours students studied for a test and students' marks in the test. Okay, so that is what is given to you. So how many students we are studying here? It's 10 students. Our sample size is 10. Okay. For each student, we are collecting two pieces of information. How much did they study and what marks did they get? So two variables for each student. Now, box plot, to make box plot, one variable will be on the x-axis and the other will be on the y-axis. It doesn't matter right now which one you plot on the x or y-axis. So I'm going to write students and number of hours they study. On the x-axis and their marks on the y-axis. I'll scale each axis based on what I need. So I have minimum, I need minimum 3 and maximum 8. So I'll plot it that way. So I'll begin with 3. Can just, I don't have to unnecessarily draw a blank line. I don't have to go farther than 8 because that's the maximum of our students study. So the lowest mark is, I think, 50. So I don't have to draw from 0. You could draw from 0, but I'm not going to. So let's say this is 50, 60, 70, 80, 90, 100. I typically hear only three or four voices when I ask questions. Hopefully others are understanding. If you're writing in chat, I'm not looking at those, I can't. But I would like that most of you participate. Okay, so now we'll plot each data point. So our first data point is this, 50 and 70. This is, we're calling it X, we're calling this X, this Y. So, you write X comma Y, that is 5 in this first, for first student, it is 570. That's how you write it, but I'm not gonna do it for all. So 570, that means 5 hours of study and 70 marks. Where do these two meet? Let's say here. That is our first data point, 570. Okay, then our next data point is 368. 3 is here, 68 is here. Then I have 465. Then I have 5.58. Sorry, 5.578. Should be using smaller. Okay. 895. $682. And 7.594. $350. $573. Oops, I didn't draw 350 right.
Yeah, yeah.
$573. Somewhere here. And then I have 4.575. You don't have to write all these points. Okay, that's your scatter plot. I'm going to actually remove all these points so that it's not so messy. This is our scatter plot. You'll notice there are 10 points. There should be, I plotted 10 points there. So that's basically kind of shows there is some sort of an increasing trend, right? Yeah, there is a bit of variation, but there is an increasing trend. So the more the students study, probably the higher their marks are. It's not necessarily saying that studying more causes you to score higher. Maybe it is true, but maybe not. It only means that the higher the students study, the more the students study, the higher are their marks. What is the reason behind it? This data does not tell us that. So it's a relationship that we are studying, but it's a very useful graph. What can we see from this? We see a trend. So I've drawn a trend. It is an increasing trend. We could also, in some other data, if there was another data, the trend may look like this. You make it something like this. Then there is a decreasing trend. Decreasing trend, right? So this would be negative relationship. This is positive relationship. Here, when X increases, Y is decreasing. Here, when X is increasing, Y is also increasing. Okay. Then you can see the strength of our relationship. How strong, how much does it hold, this relationship? How true is this relationship, you can say. That basically is seen by strength of our relationship. And the strength is how close are these data points to this line, the line that is going through its center. how close are the data points to it? The closer they are to this line, the stronger is the relationship. The more predictive is this relationship, the more confidence would have in this relationship. Okay, so if the points are, all the points are on the line, let's say if we plotted a graph and we saw our line looks like this, our data points look like this. And if I wanted to draw a line through this, this would look like something like this. Every single point is on the line. This is a perfect, and because it's going upward, positive, perfect, positive relationship. This is the strongest positive relationship possible. If it was like this, let's imagine this is a straight line. Okay, this is again perfect because it's very strong, strongest possible, perfect, negative relationship because it's going downwards. But every single point is on the line, so it is very, very strong. It's the strongest possible. So strength is how close these points are to this line that goes through the center of our data. If it looked like the one that we have, it's not perfect positive, but it is very strong. Most of the data points are pretty close to the data set, very strong positive relationship. You may see something like this. Like this, if I draw a line through its center, let's say this line goes through its center. We'll learn how to draw this line, but let's imagine this is the correct line. You see that, yeah, it has a positive trend, but the data points are not that close to the line. They're all scattered all over. So this is medium strength, let's say, quite subjective. Okay, we may see something like this. Right, you barely can see a relationship here. You'll say weak positive relationship. You may see something like this. Almost like a circle, right? What do you say? No relationship? Right? So it is still subjective. What is medium, what is very strong, it's still quite subjective, but it gives you an idea how strong the relationship is. And this graph will become very, very helpful to you in the rest of the chapter today, or at least the next part. So plotting the graph is very simple, but it gives you tremendous amount of information. It tells you if it is going to be a positive or negative relationship, the strength of the relationship, the shape. Another thing that we want to know, and this we can do only after plotting, is we can see if it is a linear relationship or a non-linear relationship. Your data may look like this. Something like this. Drawing a straight line through this data would make no sense. This is not the trend of this relationship, right? So if I really have to draw the trend, it will look something like this. Non-linear relationship. Very important, because there are certain type of analysis we can do only on linear relationship. If we have a non-linear relationship, but we did not plot it, so we don't know that there's a non-linear relationship, and we calculated something that was supposed to be for linear, that makes no sense, right? So plotting is very important to see if it is a linear or non-linear relationship, at least that much. Then we can see if there are any outliers or influential points. Now, what is outlier? What is influential point? This is basically, we just talked about outliers in a univariate analysis. Now we are going to talk about outliers in a bivariate analysis. We actually use two separate words, outliers and influential points. For this, idea is the same, but they're slightly different from one another. So outlier, and you should write this down, outliers are far on the x-axis, and they make the relationship weaker. So I'll explain what that is. Influential points are far on the x-axis, and they make the relationship weaker, make the relationship stronger. So why don't you write this, and then I'll explain.
Yes, ma'am.
Okay. Now, what does that mean? Outliers are far on the y-axis from the rest of the data set. Okay. So if our data set, if we had this box, sorry, biplot, looks like a pretty strong relationship, but we have this point as well. This data point, vertically looking for the same point, from these data points at this x, they are far vertically, right? That means on the vertical axis, on the y-axis, they are far, they're higher or lower. There could be a data point here, right? Again, it's far from the rest of the data set on the y-axis. So vertically, it's up or down, too high or too low. This is called an outlier. Now, because of this data point, this relationship suddenly becomes a bit weaker. If this data point was not there, this looked like a pretty strong relationship. But because this data point is here, it is making it appear slightly weaker. Okay. On the other hand, if your data set looked like this, if your biplot looked like this, it looks like there's almost no relationship. Maybe just a little bit positive, but barely any, very weak positive or almost no relationship. But now if there is a data point here as well, suddenly it draws this line in this direction. Suddenly it starts to look stronger than it was. So this data point that is far from the rest of the data set on the y-axis, on the x-axis, horizontally, it is far. This would be called an outlier. So ever in doubt, because I notice students get, get this question wrong quite a lot in practice and quizzes and exam, revisit this portion of the lecture. Okay, the recording will be there. Just revisit. So this is an outlier. Sorry, this is an, my bad, influential point. A data point that is far on the x-axis, horizontally from the rest of the data set, and they make the relationship appear stronger than it actually is. If this data point was not there, there's almost no, it would have been a very weak relationship. Okay, that is an influential point. Any question?
No, ma'am.
Not hearing any. Okay, let's move on then. Now we are going to calculate something called correlation coefficient. Correlation coefficient, very important. Everything is important, obviously, but it's hidden here, so I wanted to highlight. Correlation coefficient, R, its symbol is R, small or capital, doesn't matter, but that is correlation coefficient symbol. It is a measure of statistical linear relationship between two variables. So we have done biplot or scatter plot, but the strength of the relationship, we were just getting subjective idea if it is weak, strong, or anything. But correlation coefficient can actually tell us how strong is the relationship. It also tells us if it is positive or negative relationship. So its value is positive, it's a positive relationship. Its value is negative, it's a negative relationship. Okay. But it also, we can actually calculate the strength of the relationship. It is used only when the relationship is linear. That means you must first plot your data to see if it is a linear relationship or not. If it is a linear relationship, only then you should calculate R. Otherwise, you should not. It will be meaningless. Okay, so it is a measure of statistical linear relationship between two quantitative variables. We are doing quantitative analysis. We can never find out R for categorical variables. Okay, so it is always between two quantitative variables, and it has to be a linear relationship. Only then we can calculate R. So here is the formula, fun formula. R is equal to 1 over n minus 1. It is again the same degrees of freedom we have talked about before, times sum of, right? This symbol is for sum of xi minus x bar times yi minus y bar divided by sx times sy, where I goes from 1 to n. So we'll find the sum of all of this. So for each data point, we'll calculate this and then we'll add them. Or a simplified way to write is, we can actually bring this sx and sy outside. Sx and sy are standard deviation of variable x and y. So 1 over n minus 1 times sx times sy. So this we can do for the entire data, times sum of, for each individual data point, we'll have to do xi, whatever the data point is, minus x bar times the corresponding yi minus y bar. X bar and y bar are the means of the variable x and y. So this is, I think, a more simplified form of this formula. So you should be able to use this. So let's find the standard, the R for the data set for which we made the box plot, the biplot. So this was our data. 5, 3, 4, and this was our data, right? So I'm gonna use this. I'll write it down for you. Give me 1 sec. Take a picture of this data. So here's our data set. I'll write X and Y. So X, first X is Y, 5, Y is 70, then 3, 68, 4, 65, 5.5, 78, 8, 95, 6, 82, 7.5, 94, 3, 50, 5, 73, 4.5, 75. Okay. So that's our data set. Now, what do we need to do? We need to find the mean and standard deviation of X variable and the Y variable. So why don't you go ahead and find X bar and standard deviation for X variable, Y bar and standard deviation for the Y variable. Go ahead and do it quickly. Then mean and standard deviations.
Mean for X is 5.15.
Yeah, I've written these here. Just confirm that you
Oh.
have the right answers.
Okay.
Just check. So these are the correct answers for mean and standard deviations for X and Y variable. Now, what do we need to do? we need to find these first and add them up and then divide by these, right? So let's first do xi minus x bar times yi minus y bar. So for each data point, we need to calculate this. So x1 is 5 minus 5.15 times yi is 70 minus 75. And keep doing this for all of this. Fun stuff. Have fun doing this. Once you do it, you'll get approximately 190, approximately 188.89.99, something like that, or 190, let's say. And we should get approximately 0.93 positive. Don't worry if you're wondering, how did I get this so quickly? I used a shortcut, okay? This would obviously take time to calculate, but that's the point I'm trying to make here. If you had 3 minutes or 3.5 minutes per question on the exam and you had to do this math in 3 minutes, that would be hard. And still you may end up making a mistake and getting the wrong answer, right? But this would be the value of R. So we'll talk about this and we'll talk about some shortcuts as well after a 20 minutes break. So let's meet back at 4:45. Let me give you 24 minutes break. Finish this off and then take a break until 4:45. I'll see you then. Stop. stop the recording. Please, after the break, tell me that I have to start recording if I forget. Last week I forgot. Okay, let's get started. So let's talk more about this correlation coefficient. What does it tell? What are its properties, when to use it, when not to use it. So we found this correlation coefficient. The value of correlation coefficient will always be between -1 to +1. It can never be below -1. It can never be more than 1. So if we ask, which is the statement correct? The value of R is equal to -1.85.
I can see your screen.
You cannot see my
Ma'am,
screen?
we haven't shared the screen.
I never stopped sharing my screen. How did I stop? Okay. So the value of R is always between these two. If we gave you a statement that is the statement true or not, the value of R between X and Y was found to be -1.85. Is it possible? It's not
No.
possible. It is always between -1 and 1, right? So if you are calculating R and you're getting value -1.85 or something like that, you know you have made a mistake because it cannot be less than -1 or more than 1. Now, R is a ratio. If you look at its formula, if you pay attention to the formula, the units of this xi minus x bar would be the same as unit of x bar, right? They cancel out. Unit of yi minus y bar would be the same as unit of sy. They cancel out. N has no units. So R has no units. Okay. So if we gave you a statement saying that the value of R between X and Y is 0.93 square meters, makes no sense. It cannot have any units. R should always be, as I told you before, should always be calculated when there is a linear relationship between two quantitative variables. It has to be quantitative, right? Because how do you find mean and standard deviation of categorical variables? That's impossible. So you need mean and standard deviation that you can calculate only for quantitative variables. But it must be a linear relationship. You should not be calculating R for nonlinear relationship. So first draw the scatter plot. Since it has no units, changing the units of any of the variables will not change the value of R. So for example, you had kids' height and age plotted and you've calculated R. And now initially you found kids' height in inches. Now you say, oh, I want to convert into meters. You convert into meters, the value of R still would be the same. So changing units will not have any impact on the value of R. R is not robust or it's not resistant to outliers. So if there are remember when I told you, if there is an outlier that reduces the strength of the relationship, so that means it reduces R as well. And if it is, if there are influential points, then that increases the strength of the relationship, so it increases R as well. So what does R really show you? This value of R shows you the direction and strength of the relationship. So if it is positive 0.93, then it is a positive relationship. If you got negative 0.93, it is a negative relationship. So this sign tells you if it is positive or negative. But then this number, so this number part, this tells you the strength of the relationship. This tells you the strength. Okay. So number tells you this tells you the direction of the relationship. Now, once you've determined the direction, now just look at the number part without the sign. That tells you the strength of the relationship. The closer it is to 1, or negative 1, the stronger is the relationship. Okay, closer it is to 0, the weaker is the relationship. So if you're getting 0.93, that is pretty close to 1, pretty far away from 0. That's a strong relationship. These two, if there was one X and Y, the relationship was positive 0.93, the other one was negative 0.93, which one is stronger? Which one is stronger between these two?
The positive one,
Why?
because of the positive relationship and the strength as well.
I'm asking which one is stronger? They have the same strength, right? This
Yes.
number indicates the strength. This number indicates the strength. They have exactly same number. So they are exactly the same strength. Yes, one is positive, one is negative, but the strength is the same. One may look like this, right? The other may look like this. Same strength, but one is positive, the other is negative. For both, you will get 0.93, but this one may be 0.93, and this may be negative 0.93. Okay, so don't get confused. Remember, the number part tells you the strength of the relationship. Ignore the sign. Sign only tells you the direction of the relationship. So looking at R, you can determine how strong or how weak the relationship is. Biplot also gives you some idea. Now, you notice this was a long calculation. It takes time, and still you may end up making a mistake. An easy way to, in a multiple choice question, an easy way would be to guess the R value of R. Make an educated guess. Draw the scatter plot. If you draw the scatter plot, like we did here, if you look at the scatter plot, it looks like a pretty strong relationship. It's not perfect. So let's say your choices were, for this question, your choices were, what is the value of R? Let's say you don't want to do all this calculation. Choice 1 is positive 1.0. Choice 2 is negative 0.85. Choice 3 is 0.93. D is, let's say, 0.29. These are your choices. Now, if you draw the scatter plot, this is the scatter plot we drew, you know it is a positive and pretty strong relationship, right? It is not perfect. Not every point is on the line, so it's not going to be positive 1. It's not going to be negative 0.85. Now the choice is between these two. You look at it, looks pretty strong. So you say it's most likely this one, right? If the choices are very close, if I gave you 0.93 and 0.85, now the graph is not going to help because graph is quite subjective. Then you'll have to calculate. But if the choices are not that close, then you should be able to do an educated guess. Drawing a graph is a lot easier than calculating all of this, especially if it's a multiple choice question. But having said that, you should be able to do this math if you have to. Now, I'll tell you, your calculators have a function to calculate R for you. So that is up to you. If you want to use the calculator, just like we use for standard deviation, search up on the internet or the guide that you got with your calculator, see how you find R using your calculator. So you can do that as well. So that's how I did. When I got this number, I actually used my calculator to find this, and I back calculated to this. So that is R. Any questions so far? Very important stuff. Remember, these properties, this theory is equally important. Yes, you should be able to calculate, but you should know what all of this means, where you can use it, where you cannot use it. Okay, now, when you calculate R, as I told you earlier, that when you look at, biplot, that doesn't really tell you this causes this. So don't draw a conclusion like, oh, I got a very strong relationship between number of hours students studied and the marks they got. So studying more causes you to get better marks. Maybe it does, but just getting a high R value does not automatically mean that. On the other hand, let's say I calculated R for students, how many hours did they spend on social media on the day before the exam, and the marks they got in the exam. Okay, now I may find a negative relationship. The students who spent a lot of time on social media, they got lower mark. Maybe I get a very strong negative relationship. Now, that does not mean that spending time on social media causes you to do poorly. Social media is not, hopefully, not messing up your brain in a way that you get, you do worse at learning, right? So it may not be a cause and effect don't conclude that it is a cause and effect relationship. My thinking is that if you're spending a lot of time on social media on the day before the exam, you have less time to study. You're tiring your brain by spending time there, and you have less time remaining to study. And that's why is a relative relationship. So there is a third thing, that is, we are talking about how much time did you have to study, basically. That is more likely to be the cause of lower marks as compared to spending time on social media. But we may find a negative relationship between these two variables. So big caution, do not assume that it is a cause and effect relationship. This does not mean a cause and effect relationship. Okay, you can calculate R between any two quantitative variables, but that does not mean there is actually a meaningful relationship between those two values. Okay, let me give you some examples. Oftentimes there are lurking variables that make the interpretation, that's why you need to be careful about the interpretation of your value of R. What is a lurking variable? A lurking variable is a variable, remember variable, that we are not studying the effect of, but is actually affecting one or both of the variables that we are indeed studying. For example, I said social media, time on social media, and marks, right? I'm finding negative relationship between these two, strong negative relationship between these two. But there's actually another variable that is impacting how much time you are spending on social media, or that is impacting how much time you're studying. It is studying that is most likely impacting your marks, not the time on social media. So this could be a lurking variable. Lurking means something that is hiding, it's in the background, but it is impacting and not the other way around. So how much time you have to study, that is determining how many marks you get. But because you're losing time by spending time on social media, you are seeing a negative relationship, right? So we have to be mindful. We should not be drawing, cause and effect sort of conclusions from strong values of R. So a researcher collected the data as below for elementary school children. So that is kindergarten to grade 6 in Canada. Their children's shoe sizes and their scores in a math test. So what happened? This researcher went to an elementary school, went and measured children's school sizes, randomly some children, and gave these children a math test. And then studied the relationship between their shoe sizes and their marks. And he found a very strong positive relationship, or let's say he found was 0.92. It's a very strong positive relationship, right? Does that mean the longer the children's feet are, the better they are at math? That would be a bad conclusion, right? If you did cause and effect, you're basically saying that having longer feet causes you to do better in math. If that was true, if people interpreted it that way, parents would be stretching their kids' feet every night, making sure they get longer instead of teaching them math. So be careful. But is there a lurking variable here? Can you think of, if there is a lurking variable, what might be behind this? Why do you think there is a strong relationship between these two, even if there should not be any cause and effect? Any guesses? Thinking helps.
Maybe because of the age.
The older the child is, the bigger their shoe size is likely to be. The taller they are, the bigger the shoe size, most likely, right? And the older the child is likely to be in higher grade and should be doing better in math. So a grade 5 kid should be doing better than grade 1 kid, right? So age could be a lurking variable here. Good. It is age that is impacting one or both of the other variables. It is impacting both, in this case, the shoe size as well as their ability to do math. Okay, here is another example. A city collected data and they found a strong positive relationship between the number of firemen present at a fire scene and the amount of damage caused by the fire. So they found a very strong positive relationship between how many firemen were present at the fire scene and how much damage did that fire cause. And they found a positive relationship. That means the bigger the fire there was, the more the more the firemen were present, the bigger the damage it caused. So if you're looking at a cause and effect relationship between these two, your city should fire the entire fire crew. Say, oh, the more of you are present at a scene, the more damage occurs. We don't need you. What might be the lurking variable here?
The size or the amount.
Yeah, the
of
size
fire.
of the fire. The bigger the fire, the more firemen would be sent, right? So the number of firemen would be higher if the fire is big. And if the bigger the fire, the more damage it would cause as well. That doesn't mean firemen are causing the damage, right? So it is dangerous to think that there is a cause and effect relationship just because you found a very strong relationship between two variables. Now, we will be talking about. Okay, so what if we see a relationship? So what? What do we do with that? We do regression analysis. If we know that there is a meaningful relationship between X and Y, so we have found, for example, students' marks and number of hours they study. Yeah, it makes sense. The more they study, the better their marks are, right? Logically, it makes sense. So it is a meaningful relationship. Then we can actually use this relationship to predict. For example, you say that I want to get A+ in this course. How much should I study? And I look at past data and I do some analysis based on the relationship between number of hours students study and the marks they got. I say that to be able to get over 90%, you must study for at least 8 hours or whatever, right? So I'm giving you a prediction that if you study this much, you are likely to get this many marks. So I'm making a prediction. It's not just in my head, I'm actually using an analysis called regression analysis on the past data, students' data. Based on that, I want to be able to predict the value of Y variable based on X variable. Now here we have to be careful. I told you when we make a biplot, we could plot X or Y on any, the variable on any axis as we like. But when we do, now that we have concluded that, okay, there is actually a meaningful relationship between X and Y, such that we can use this relation to predict one variable based on the other, then we have to define our variables carefully. One variable will have to be X variable, the other variable will have to be Y variable. We cannot interchange them. So it is extremely important that we identify which one should be X variable and which one should be plotted on the Y axis. So X variable is also known as explanatory variable. Okay, X for X, you see X in here, so it sounds X. Explanatory variable, maybe this will help you remember. This is the independent variable. This is the variable that is impacting the other, not the other way around. So when you are looking at students' marks and number of hours they study, which one do you think is the X variable? What impacts the other one? Will your marks impact how much you study, or it is the other way around?
It's the other way around.
It is the other way around, right? How much you study will impact your mark. What do you want to predict? You want to predict a student's mark based on how much they studied. So how much mark they will get is dependent on how much they study, right? So independent variable would be how much they study. Dependent variable would be what marks they will get. Okay, so independent variable is always plotted on the x-axis. On the x-axis, independent variable. On the y-axis, we have the dependent variable. Independent variable, we also call it explanatory variable, or X variable, or you may also call it a factor. We'll talk about factors in the next unit, but that's another term we can give. So quite a few names. This is the one that is explaining what is happening to Y. That's why it's called an explanatory variable. It is always plotted on the x-axis. That's why it is also called X variable. Okay, that is the independent variable. Y variable, on the other hand, is plotted on the y-axis. This is the dependent variable. It is also known as response variable because this responds to what X is. So if you study 5 hours, in response to that, your marks would be something. So marks are responding to how much you study, right? So that is response variable. It is also called predicted variable. predicted. This is the one that we want to predict. So the one that we want to predict must always be on the y-axis. It must always be the y variable. It's extremely important that you recognize which variable is which. Sometimes we'll say to predict a person's weight based on this data, do the regression analysis. If you're predicting people's weight, that means their weight is the y variable. Right? We've given you a hint there that we're predicting people's weight by this regression analysis. So that means the weight in that data, the weight would be the y variable. So you have to be, before you begin regression analysis, ask yourself which one is x and which one is y. And why do you think that is the case? Is there any hint given in the question, or do you have a logic behind it? Okay. So when you study regression analysis, must first know which one is x and which one is y. Do not do anything about regression before you know this. Otherwise, you'll mess it up. So when we do regression analysis, our purpose is to create a prediction equation, create an equation such as y is equal to x plus, not x plus, a plus bx. A and b are constants. Let's not write constants, but these are values, numbers. Okay, we'll talk about what this is. So this is an equation. If you know this and this, for any given value of x, you can calculate y, you can predict y. Okay, so we'll see how this works out. Don't write this equation yet, because I'll give you a different form of this equation. So, to create this equation so that we can predict y based on a given value of x, as long as we have those a and b. Okay? So as an example, let's say I found that students who do good in the midterm also do good in the final exam. That's what I found. I found a strong positive relationship between midterm and final exam. Now, even if it is not a cause and effect relationship, it is a meaningful relationship, because students who study a certain way, they do better in both. But there would be some students who, did well in midterm but did not do well in final, or the other way around. But generally, students who do good in midterm, they also do good in the final. So I find a, let's say, strong positive relationship based on my data. So I do regression analysis. Okay, and I create an equation. We call it regression equation, or least square regression equation, or best fit equation. This equation I will use to calculate, if you ask me, okay, I got 82% in the midterm. What should I expect to get in the final exam? I say, okay, if you study the same way, the way you did, then maybe based on my analysis, you will get 80.5 on the final. It's not a guarantee, this is my prediction, right? You may or may not study the same way, you may not get 80.5, but that's my prediction for you. So how did I do that? I used a regression equation. That regression equation is based on my past data, where I found a strong relationship between midterm and final exam. So let's say this is what this equation looks like. This is what this equation looks like. Predicted final exam mark, remember this is y, and because it's predicted, we put a hat on it. Putting a hat on it means predicted. Predicted final exam mark, which is the predicted variable, y, is equal to -10 plus 1.1 times midterm marks, which is our variable x, independent variable, right? That's the equation here. Y hat is equal to a certain number plus or minus certain number times x. Remember, I gave you this, y is equal to a plus b x. It's essentially the same format, but here these numbers are, what are these numbers? We'll talk about that. And how do we get these numbers? These are from past data. So if I have this, calculated this equation, right? If I've calculated this equation, then you want to know that you got 82% marks in the midterm. So this was your midterm mark, this was your X variable. You want to know what is your predicted final exam mark. So predicted final exam mark will be equal to -10 plus 1.1 times 82. That's based on this equation. So I calculate and I get 80.2. So I say, well, my prediction is that you'll get 80.2 on the final exam. Okay, it's a prediction, it's not a guarantee. So how do we find this equation? In the equation, what we have to do is we have to find this, and then we have the equation. What are these? This is called intercept, y-intercept, and this is called the slope. Now you have heard about these terms. If you've done algebra, linear algebra, you have learned linear equations. Maybe in your case, the linear equation look like y is equal to a plus bx, like this. This is the intercept, and this is the slope. Or you did y is equal to c plus mx. Again, this is constant intercept, and this is slope, or you might have called it gradient. We'll call it slope. Okay, so slope and gradient. First of all, what are these? And then how do we calculate these? So let's not now talk about this equation. This equation, remember, it is called least square regression equation. Least square regression equation. We can also call it regression equation as a short. This is also called best fit equation or best fit line. We'll talk about why it is called so, why these names. It is also called prediction equation because we use it for predicting y value. Okay. So now, what is it? Least square regression equation. In stats, we use this terminal, these symbols. For y hat, remember this is predicted value of y, is equal to b naught, b0. Instead of a, we write b0 plus b1. b1 is slope. Okay, so this is intercept, this is slope, this is the actual value of x, and this is the predicted value of y. So if we have calculated b naught and b1, then we have the equation, right? If we calculate b naught is equal to -10, b1 equal to 1.1, then our equation becomes y hat is equal to -10 plus 1.1x, right? That's what it becomes. So how do we find b naught and b1? That is based on the past data, based on which we are predicting. So what is y-intercept? This is y-intercept. What is it? B naught, what is it? And be careful, we will ask you what does it mean. You should be able to use that interpretation. It is the predicted value of y when actual value of x is 0. So this is a linear equation. What does it mean? It's a linear equation. Basically, once you have this equation, you can draw a straight line with a certain slope and intercept. Let's see. 10, 20, 30, 40, 50, 60. Let's do it here as well. Now, let's say this is our equation. We'll see how we calculate it, but just let's first understand what does it mean. This equation I can use to draw a line on this graph. I can use any value of x, let's say, when x is equal to 10. What is y hat? Can you calculate that for me, please?
One.
Can anybody calculate this quickly?
Yes, ma'am. It's 1.
It's 1. Okay. So that's 1 point I got. When x is equal to 10, predicted value of y is 1. That's 1 point I got. I can plot this on this graph. When x is 10, value of y is 0.1. So I can plot it here, this point. Okay. Now, when x is equal to, let's say, 30, what is the predicted value of y? Can you calculate that?
23.
23, right? Put the value of x here, calculate y hat. So 23. That means I got another point on this line, which is 30, 23. That means x is 30, y is 23. So that point is, let's say, here, right? I've got 2 points. Just using any random value of x, I've calculated y hat. Now, once that I have these 2 points, I can connect them with a straight line. And this line can be extended in any direction. This is a linear equation. This equation essentially means the same thing. So once we have the equation, we can draw a line, right? You've done this in linear algebra, most likely. So what is y-intercept? Y-intercept is the predicted value of y when x is equal to 0. So let's put y hat, this is predicted value of y, is equal to -10 plus 1.1 times x is 0. So obviously y hat is equal to -10, right? So how do you plot it? When x is equal to 0, what is the value of y? If you look at this line, it is at this point. It's a negative -10, right? It would come somewhere here. Obviously, I've not scaled it well, but that's how it would come. So that's what it means. It is not an actual value. We should, we'll see the precautions of using this graph, but this is what the intercept means. The predicted value of y when x is equal to 0. Okay. So on graph, this is what it would look like. Then what is slope? Again, by how much does y change on average when x increases by 1 unit? Now, change. Let's say when x is equal to 30, y is equal to 23, right? So when x is equal to 30, y hat we just calculated is 23. What happens when x is equal to 31? Y hat would be how much? We're getting 24.1.
Yes.
Okay, so when x increased by 1 unit, this is 31, this is 30, so there is 1 unit increase. How did y change? It increased by 1.1 units. That is exactly what the slope is on average. So on average, what we'll see, if let's say all students study 1 extra hour, we'll see an average increase of 1.1 unit in marks. Okay, or if they got 1 extra mark in midterm, all the class got 1 extra mark in midterm, on average, we'll see an increase of 1.1 mark in the class. It is average. It is not that one particular student gets 1 extra mark, that particular student now gets 1.1 extra mark. That's not how it works. Okay, so it's average. On graph, how does it look? This is 30, right? When 31, this point is like, let's say here, I know this is too tiny. So this difference between this point and this point, that is essentially what is slope. This little tiny difference between, so this was 31 for 24.1, right? That second point. The vertical distance between these 2 points, that is the slope. Vertically, slope is between this and this tiny distance that is equal to 1.1. So that is slope. The bigger the slope, the steeper the line would be. That's bigger slope. The smaller the slope, the flatter the line would be. This is less slope. Okay, so slope is obviously technically slope. What you mean is slope. So, but you should be able to interpret it this way. What is slope? That is, by how much does y change on average when x increases by 1 unit? If it is a negative relationship, slope will be negative. If it's a positive relationship, slope will be positive. Know that. So we have a few minutes, so we'll finish calculating this regression equation, so that in the next class we can finish off this unit and go over third unit as well. Then we'll catch up. Then we'll have caught up. Okay, so how do we calculate R? Regression equation. So all we really need to do, we need to find B naught and B1. We know what they mean now. B naught is the y-intercept, B1 is the slope. We know what they mean, but now we need to be able to calculate it on past data, right? So how do we do that? B1 is equal to SY divided by SX times R. So you need to be able to calculate SY, SX, and R. Remember, those calculations are long. Learn how to do it on your calculator. In a question, we may give you just the data, and now you have to do all of this. That obviously would take a lot of time. Calculator would be very handy, but we may actually give you the value of R in the question so that you don't have to do that math. Okay, but it'd be a good idea to learn how to do this on your calculator if you can. Now, SY over SX times R. SY is sample standard deviation for Y variable, SX is the sample standard deviation for X variable, R is the correlation coefficient. Once you have calculated B1 using this for the data, then you can calculate B naught. So first calculate B1, then calculate B naught, because B naught is coming from this property of this equation. The property is Y bar is equal to B naught plus B1 X bar. Remember, bars are for mean. So what this essentially is saying, that this basically means the regression line always passes through a point called X bar, Y bar. This point, whatever X bar and Y bar are for our data, the regression line will always pass through that, and that's why this is true. And based on this, we can, rearrange it this way to find B naught. So first find B1 and then find B naught based on this relationship. And that is how you find regression equations. Once you have B naught and B1, you can write the equation this way. So why don't you do it for this data set? Now, just to make your life easier, I am giving you R here.
Miss, it's 18.74.
What?
SY.
I'm getting 1.85. Oh, hang on. You might be right. Sorry. I didn't read it correctly. 18.75. Yeah, you're right. I wrote as 6 there.
Professor,
Mhm.
is it necessary to get the values exact? Like,
No, you will get slightly, you'll get slightly off. I've used calculator to do all of this, so mine is going to be more accurate. But if you get around 15.99 or 16, that would be
yeah,
fine. Or yeah,
yeah.
that's fine. Yeah, that's rounding off error. That's fine. In a multiple choice question, you'll be able to, find the right one.
And
Close it up.
ma'am, for this type of questions, if how many decimal places are we supposed to write down?
You're doing multiple choice, right? So
Yeah.
you don't decide how many decimal places. The choices are already given to you.
Oh,
We
okay.
typically use up to 4 decimal places.
Okay.
Okay. So now you can write the equation. The equation would be actually like this. The equation would be y hat is equal to b naught. B naught is 16.03 or 16 plus 9.73. So it is definitely a positive relationship because your slope is positive. Intercept can be positive, negative, doesn't matter. It is a slope that tells you the direction. Remember, because slope has, remember, B1 is equal to R times SY over SX. SY and SX both are positive. R can be positive or negative. So whatever is the sign of R is going to be the sign of B1. Okay, so you can check that as well. So that is your equation. Based on this equation, can you calculate, can you predict a student's marks if a student studied for 3.5 hours? I'm getting about 50. To be accurate. Any question about it? So based on this equation, you're predicting that a student who studies for 3.5 hours would get 50 marks. Okay, that is a prediction, not a guarantee. Can you do it for 6.8 hours quickly?
82.19.
Okay, let me just make sure. Yeah, 82.194. Right? So it's simple. 0 hours, and I said, don't do this. And I'll tell you why in the next class. Okay, this is enough for today. So here, if I asked you, you calculated this equation. If I asked you interpret, let's do this. Interpret the intercept and interpret the slope. So we are basically, interpret means tell us the meaning. So you got, what is the intercept here in this equation?
9.73.
Intercept
Oh, sorry, 16.03.
16.03. So what does the 16.03 mean? What is the meaning of it? It means that when X is 0, this is the predicted value of Y. But what is X? X is number of hours students study. When a student studies for 0 hours, the predicted mark is 16.03. That's what it means. That's the meaning. You should be able to write it something like this. Similarly, what is the slope? Slope, remember, slope means when x changes by 1 unit, increases by 1 unit, on average, what is the average change in y? Okay, it could be positive or negative, but what is the average change in y? So when x increases, x is number of hours students study. Even student studies for students study 1 extra hour, the average increase, because it's positive, in the marks will be 9.73, because that is the slope. Okay, so you must know what it means. You must be able to interpret it like this, not just calculate, but also interpret. Very important. Okay, so that would be our lecture for today. I'm going to record your attendance now. Anybody who did not do the activity? Everybody did it? I'm going to check anyways, but I thought I would ask you. Okay, let's record the attendance then.